Today we will introduce Newton's laws for angular motions. Let's start by recalling briefly that a couple created by two equal and opposite forces with different lines of action separated by a distance d can cause a rotation because those forces generate a moment. The moment has a magnitude m0 of the magnitude of f times d. And further, in general, the moment due to a force F acting at a position defined by the position vector r from the origin is the vector m0 equals r cross F. Note that the orientation of the moment vector is the axis about which, in a right-handed sense, the moments act to create rotation. Newton's laws also hold for moment, angular velocity, angular acceleration, and angular momentum, as they do for force, velocity, acceleration, and momentum in linear motions. So let's start by defining those quantities.
So let's consider the rotation of a rigid body about an axis defined by the unit normal vector n, which is normal to the plane of rotation of point P. Point P has position vector r, and r makes an angle phi to n. The position of P is theta, and the velocity vector tangent to the circle v is dr dt, or r dot. Now the magnitude of v is ds dt, where s is arc length around the arc, which would be r d theta dt. Now r here is the radius in the plane of rotation of the point P, which is therefore r sine phi. So therefore ds dt equals little r theta dot sine phi, where little r is the magnitude of the position vector r, and theta dot is the magnitude of the angular velocity vector omega. So the magnitude of the velocity equals the magnitude of the radius times the magnitude of the angular velocity times sine of phi, where the angular velocity vector has magnitude theta dot and direction n. Now, if we make the construction omega cross r and take its magnitude, then its magnitude would be the magnitude of omega times the magnitude of r times the sine of phi, which is ds dt, which is the magnitude of v, as we found above. Therefore, given that v is perpendicular to the plane of omega and r, we can therefore write that omega cross r equals ds dt times the unit vector v divided by the magnitude of v, but ds dt is the magnitude of v, so therefore omega cross r is v. And so we now have a vector definition of the angular velocity omega in terms of the position vector and the velocity vector. So v, which is r dot, is omega cross r, where the magnitude of omega is theta dot. The acceleration a is dv dt, which from our previous slide is d dt of omega cross r. Applying the product rule is d omega dt cross r plus omega cross dr dt, which is d omega dt cross r plus omega cross v. And d omega dt is alpha, the angular acceleration vector, so we get that a is equal to alpha cross r plus omega cross v. So the angular acceleration alpha also acts along the axis of n, and its magnitude is omega dot or theta double dot. Now making use of, again, V equals omega cross R, that gives us that A equals alpha cross R, and substituting omega cross R here, we get omega cross R. And so looking at the direction of this vector, we can see that these are the tangential component of A, and that this term here is the radial component of the acceleration.
In angular motions, the mass in linear motions becomes the moment of inertia I, also known as the angular mass or rotational inertia. And it represents the effect of masses on rotational inertia. For a system of n masses, each labeled mi, with I equals 1 through n, each with a perpendicular distance di from the axis of rotation of the system of masses, the moment of inertia I is the sum from I equals 1 to n of mi times di squared. Angular momentum, by analogy with linear momentum, which is mass times velocity, is I times angular velocity and is labeled L. And like linear momentum, is a vector that can also be expressed as the cross product of R times the linear momentum, mv. So for a system of n particles, the angular momentum L is the sum from j equals 1 to n of rj crossed with the linear momentum of each particle, mj vj. So this now puts us in a position to define Newton's laws of angular motion. Newton's first angular law says that if there is no moment, that angular velocity is constant. So if m equals 0, omega equals constant. Newton's second angular law states that the rate of change of angular momentum balances the external moment, i.e., if m is not equal to 0, then m is the rate of change of angular momentum dl dt, or d dt of I omega. And since the masses and positions are not changing, then that would be I alpha, the angular acceleration. So this is the angular equivalent of F equals ma, which is m equals I alpha, or m minus I alpha equals 0. Newton's third angular law for a system of particles, I equals 1 through n, states that for every moment interaction, there's a moment reaction, or the moment of interaction of particle j on particle I, mij, is equal and opposite to the moment of interaction of particle I on particle j, mji. And therefore we can write mij plus mji must equal 0. Now we can expand Newton's second angular law, which states that the moment m is equal to the rate of change of angular momentum, dl dt, which is equal to the moment of inertia times the angular acceleration, I times alpha, when m is not equal to 0, by substituting our earlier definition of the angular momentum L, which gives us the rate of change with respect to time of sigma j of rj crossed with mj vj is equal to the sum over j of rj times fje, where fje are the external forces acting on particle j, and their lines of action have position vectors rj. The total moment acting on particle I is the external moment, MIE, plus the sum of all the interaction moments, MIJ. So therefore, MI, the moment acting on particle I, is MIE, the external moment, plus the sum of the interaction moments from j equals 1 to n of Mij. Then from the second angular law, Mi must equal dLi dt, and hence, for all the particles in the system, I equals 1 to n, we can write that d dt of the sum from j equals 1 to n of Rj crossed with the linear momentum Mj Vj must equal Mi external plus the sum of all the interaction forces, so sum from j equals 1 to n of Mij, which is therefore a system of 3 times n ordinary differential equations. Now, as we did for linear static equilibrium, for a body in static equilibrium, there is no tendency to rotate, and therefore the moment m is 0, which gives us that Mi external plus the sum from j equals 1 to n of Mij must equal 0. And summing this over all n particles in the system gives us the sum from I equals 1 to n of Mi external plus the sum from I equals 1 to n and the sum from j equals 1 to n of Mij. Now, in the same way as we did for the linear laws, from Newton's third angular law, the second term is 0 because for every Mij there's an Mji, which is equal and opposite, and the diagonals Mii are 0 by definition. And hence, for a body in equilibrium, we get that the sum of all the external moments, which would be the sum from I equals 1 to n of Ri times Fi external, so that's the moments generated by all the external forces, is 0. Hence we can state, for a body in static equilibrium, the sum of all the external moments around any fixed point is 0. So as you can see, the 3 laws of motion for angular motions completely parallel Newton's laws for linear motions, and they allow us to draw similar conclusions for bodies in equilibrium, namely that the sum of all the external moments is 0, just as for linear motion, the sum of all the external forces is 0. And furthermore, since those moments can be generated by forces, we can also write that the sum of the position vectors R times the external forces must be 0.